equations. Now let's solve an integral equation. The first time, in this class, we haven't have any integral equation. All right, so the equation, there is an integral, unknown function inside integral. How to solve? If our old way cannot solve, our old way, but with convolution, yes, or convolution, you can solve integral equation. Yeah, we only see one example here. Okay, here I only show you one example we can do. Yeah, but this kind of question won't appear in the final. Yeah, so the final, this week I will give you homework assignment number 2. Oh, sorry, number 3. Yeah, number 3, and we won't have number 4 because we don't have time for number 4. Okay, so we only have time for number 3. Yeah. Number 3, I plan to cover 6 of 8 questions. Final, we have 8 questions, right? 8 computation questions. Yeah. But this homework assignment number 3, I try to cover 6 of the 8. Yeah. So I will, let you know. Yeah. 1, 2, 3. The last 2 we cannot cover. Yeah. I just, I print out, I print out to give you some sample questions. How about that? Last 2, each one I give you 2 or 3 sample questions and the solutions. You just practice by yourself, 2 of them, okay? You practice by yourselves, sample questions. Yeah. So that's our plan, yeah. All right. First, let's look at the integral equation. Solve this one. Volterra integral equation of the second kind. Yeah. Look at this integral equation. Yeah. The second term, inside that integral, there is the unknown function y. Y of tau, it's unknown. Yeah. It's unknown. Okay? Yeah. Yeah. So people may, usually when you have integral, people like to do derivative, try to get rid of integral, right? Yeah, so that's one way, derivative. But for this one, if you do derivative, can you get rid of integral? You cannot, right? So if you do derivative, integral is still there, okay? You cannot get rid of it, yeah. All right, but here you see, if you look at the special form of that integral, you use the definition of convolution. Now, here it's, this equation happens to use the structure of convolution. Is it convolution structure? Yeah. That's something we like to take advantage of. Structure of convolution. Because when you see this convolution structure, you apply Laplace transform, you get a product of 2 functions. Product of the 2 functions of Laplace transform. Yeah. All right, so let's do it. Laplace transform, okay? Integral Laplace transform, because convolution, it should be a product of 2 Laplace transform of those 2 functions. Okay? Product of first Laplace transform, little y Laplace transform, that's capital Y. Second, the sine, yeah? So here, sine function, right? Yeah. Sine function. Sine of t, Laplace transform, this one. Did I copy the basic formula? Yeah, here I didn't copy. Yeah. But here I just, for your reference, Laplace transform of sine of omega t equals omega over s squared plus omega squared. Here, omega equals 1. Yeah. Here we use omega equals 1. Okay, yeah. So the second function, we need to take Laplace transform of sine t. That's the 1 over s squared plus 1. Okay, yeah. So that's our convolution theorem. Yeah. All right. Then this algebraic equation, very simple, right? We need to solve this algebraic equation. The inverse Laplace transform of this function. Yeah. That's easy. Yeah. Yeah. Here we use this basic formula, number 4. Basic formula number 4. Okay? Yeah. Right hand side n factorial over s to the n plus 1. N factorial, we can adjust it. Okay? New denominator s squared 1 plus 1. N equals 1. S to the fourth 3 plus 1. Okay? N equals 3. So we can apply this formula. Right? All right. Inverse Laplace transform. Yeah. Each one, the first one, apply this formula, we get a t because n equals 1. Okay? T to the n. So t, only t. Okay? Second, yeah, we need to divide by 3 factorial. So 1/6 times t cubed. N equals 3. Y function. So you can, in this simple way, you can solve that integral equation easily. Yeah. But you may argue, if we don't have a convolution here, then it could be very hard. Yeah. Yeah. It's true. Yeah. Yeah. So if you do not have the right structure, it could be very hard. Yeah. Okay. Yeah. All right. So we just see that single example. Yeah. Just appreciate the power of convolution tool. Yeah. We treat it as a tool, yeah. Special tool, problem-solving tool. Yeah. All right. Next topic, differentiation and integration of transforms. Yeah. We saw this. We studied second time. The first time. Yeah. First time, I copied the formula from the first time, and let's do comparisons. Yeah. So you do not get confused. Yeah. Because some students, you may get the impression, we learned this before. Why we learn another time, right? We learned derivative because, remember, derivative corresponds to multiplication. Integral corresponds to division. We learned that before, right? Yeah. Because when you do multiplication, division, where do you do it? Do you do the multiplication division at a time domain or S domain? There is a S domain, right? Yeah. Yeah. Okay. Yeah. Yeah. Some people may call frequency domain. Yeah. Yeah. Although it may, because hard to interpret as frequency. Yeah. But because usually the transformation convert time domain to frequency domain. Okay. Yeah. Some people, if they use frequency domain, so you know what they are talking about. Okay. So our S domain. Yeah. All right. Differentiation of transformation. Start with definition. Let's look at the Laplace transform definition again. Okay. This integral formula. Okay. Yeah. Here, just look at, yeah. Yeah. So here I draw this line. Yeah. Okay. Just look at the right-hand side of this line. Okay? Just look at the right-hand side of this. F of s equals this integral. Okay? Yeah. So both sides, we treat them as a function of s. S is the variable. Okay? We treat as function of s. Yeah. All right. Here, think about. If we take derivatives, both sides, what would happen? We take derivatives, both sides. Yeah. Left-hand side easy, f prime, capital F prime of s. Right-hand side, can you see the derivative? We get this new expression. Yeah. Let me explain it. Yeah. Because there is a theorem behind it. Yeah. Theorem behind it in calculus. Yeah. In calculus, yeah, we apply that theorem. Okay, yeah, in calculus. Yeah, but we cannot go back to. We cannot study that theorem. Yeah. So that theorem tells us. Yeah, tells us. Yeah, okay. So you have a integral. Inside the integral, you have a function with a variable s. Okay. Yeah. So then the whole integral is a function of s. Then it is possible you can apply derivative on that whole function. Yeah. If we apply derivative on the whole function, okay, yeah, derivative on whole function, that means you take ds. All right, so here I write in this way. D derivative, is it this d over ds, that integral thing, right? Yeah, integral. Okay, yeah, integral. So here you have a function. Let's say s t. Okay, yeah, dt. Like that. Okay, yeah, because that function, one variable s. That's the corresponds to this variable. Another, the dummy variable for the integral. That dummy variable. Okay, all right. Then when you take derivatives under certain condition, yeah, here there is some strict condition. Under certain condition, yeah, okay, yeah, there is some condition. Sometimes it doesn't work. Sometimes it works. Under certain condition, yeah, you can do derivative inside integral. Yeah. Although you can say, partial, yeah, because this way we can treat it as a partial, right? Yeah, you can do that way. If the function good enough, that g function good enough, okay, you can do this. Yeah. Because good enough, it means the integral should be well defined. Okay, yeah, yeah. If it does not exist, then you cannot do this. Okay, so it should be good enough, so that you can take all the operations. Yeah, but we assume our function is good enough. Okay, yeah. So we can do this operation. All right. Here, you take a partial derivative. T, you treat as constant, right? T part, you treat as constant. Partial derivative, you take partial derivative on this e term. Do you get negative t out, negative t chain rule, right? Negative t times original function, negative 1 here, another t is here. So that's the partial derivative. Okay? Yeah. So there is a calculus theorem. Guarantees we can do this operation legally. Okay? It's legal. Yeah. Yeah. All right. So, yeah, it's like that. Okay. All right. After we do that operation, we get a new formula. Can you see what's this new formula? This formula, right hand side, is it Laplace transform of a new function? The definition, Laplace transform of this t times f function. Okay, t times that f function. Yeah. So that's our new formula. All right. Yeah. 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 So, yeah. 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 You can see it. Yeah. I just leave there. Yeah. All right. Yeah. So now we can write. After that operation, Laplace transform of little t times original f function. Right hand side, we get a negative t, capital F prime of s function. Prime. Okay? That is this, differentiation here. Where do we do the differentiation? We do differentiation at the S domain, yeah, not the time domain, right? At S domain. So this formula, differentiation at the S domain. Okay? All right. So then the inverse, you can write that away. Okay? The inverse formula, just, from there. Yeah. But I like to copy our old differentiation formula so you can do comparison. Yeah. Oh, yeah, that's the, we can apply this, we can do some calculation. Yeah. But I like to let you compare our old, later. Yeah, later I copy somewhere. Yeah. Later, when we apply this formula, so sometimes when we use that version, previous version, differentiation formula. Yeah. Okay. All right. Here, we want to calculate. So here, these formulas we can calculate, but here I only want to show you one simple example, the middle one. How to calculate inverse Laplace transform of the middle one. Okay? Denominator has a square. Okay? Denominator has a square. Okay? All right. To do that, let's start with this basic formula. Okay? So we replace omega by beta. Beta. Laplace transform of sine beta t equals beta over s squared plus beta squared. That's the basic formula. Okay? All right. Then we apply our new differentiation formula. New differentiation formula. Right hand side, capital S. Can we take derivative of capital F and the negative? The left hand side should be Laplace transform of t times sine beta t. T times, by that formula. So Laplace transform of t times sine beta t equals negative d over ds on this f function, capital F function. Yeah. This one we can use the chain rule, right? So this one, I think the easiest way, we write it so inside this parenthesis, beta constant, and we write s squared plus beta squared to the negative one, negative first power. Yeah. Then you apply the chain rule. Okay. Then you apply the chain rule. Negative 1 times parenthesis negative 2 in then chain rule inside 2s. The chain rule way. Okay. All right. So because this negative 1 cancel out. So positive. Okay? 2s, chain rule you have 2s. So 2 beta s. And then denominator parenthesis square. Yeah. Square. Okay? And minus 1 square. Okay? Yeah. Now you compare with the formula inside the circle. Yeah. The only difference is 2 beta constant, right? Yeah. If you divide both sides by 2 beta constant, you get right hand side function the same as inside the circle, the function. Okay? All right. So you do that division. Division by 2 beta. So you get this formula. Yeah. Okay? But if you look at this one here, that t is missing, right? Yeah. Yeah. Because this table, I did a screen shot cut from the table, from the textbook. Yeah. So there is a t, missing t here. Okay? Yeah. Missing t. Yeah. Yeah. All right? Otherwise, we can apply our basic formula, right? If t is missing, we just apply our basic formula there. Okay? Yeah. Yeah. So here, after the computation, we know we should put a t here. Okay? Yeah. So you see the table, so you know there is an error here. Yeah. All right. That's this example here. Yeah. Yeah. All right. Let me show you a few more examples. Differentiation. I need to show you integration. Yeah. Integration formula. All right. Integration of transforms, Laplace transform. Okay, all right. Yeah, so here, Laplace transform of integral, this is our old theorem. So I copy, yeah, for comparison, yeah. Because you may ask why we study another time, right? Integration. Our old theorem, this is our old theorem, okay? When we do integration, Laplace transform here at the time domain side, this is a time domain. Yeah. So we take integral, okay? Then Laplace transform of integral at a time domain. So S domain, we don't have integral, okay? S domain, we have a division, yeah. All right, yeah. That's the old theorem. Let's look at a new integration. New integration, this is the formula. Yeah. After I show you the formula, then I prove a little bit, yeah, prove quickly, all right? So the new integral formula, I want you to compare with the older version. But one main difference is the integration occurs at the S domain, not time domain here. Laplace transform f of t over t, at the time domain there is no integral, okay? It's a division. It's a division by t. Yeah. But at the S domain, you take integral, okay? Yeah, so that's the formula. Inverse Laplace transform, yeah, so you have that version, yeah. But in order to apply these formulas, you need to make sure certain conditions are satisfied, yeah. Okay. In other words, the functions should be good enough. Yeah. Here, let me show you, let me go through all those conditions. Wow. Conditions, the first condition, f of t over t, when t goes to 0, this limit must exist. Yeah. So otherwise, you have trouble here. Yeah. So the limit must exist. So the function, you can define the function at a 0 point. Yeah. Otherwise, that function, f of t over t, at a 0, you know, you can define any value there. Okay? Yeah. Then the whole formula doesn't work. Yeah. So the first condition, this limit must exist. Yeah. So then you can do, you know, integration by parts. Otherwise, how can you do integration by parts? Right? So this limit, you need to use this limit to do integration by parts. Okay? All right. Yeah. Second condition. Yeah. We know little f, in order to make sure its Laplace transform exists, little f should be bounded by this capital M times e function, e to the kt function. There is a constant k there, okay? Yeah. For certain constant k. Yeah. So that's for the little f. Yeah. And then the formula, because formula you need to use s in the integral s. That little s inside the integral should be greater than the k in this upper bound of little f function. Yeah. Yeah. That's all the conditions you need. Yeah. But for us, we can assume our functions are good enough. Our functions allow us to do these operations. Yeah. Yeah. If necessary, yeah, we need to check these conditions. Yeah. All right. To prove it, yeah, here, let me explain the formula. Yeah. So, first, based on the definition, s tilde dummy variable, yeah, I mean integral, so any variable you can use. So we don't want to confuse it with the s here. So we use a slightly different variable symbol here. All right. All right. So by definition, this is the definition. Yeah. Laplace transform. The capital F definition like that. All right. Then here we apply another calculus theorem here. Yeah. apply another calculus theorem. Yeah. So here I just let you know. Look at, we have two integrals, right? One after another. First integral, then second integral. All right. So here there is some calculus theorem tells us we can swap these two integrals. Change the order. Okay? We can swap under some good condition. Now, if your function is good enough, we can swap. Okay? Yeah. Your function, for example, absolute integrable. Its absolute value is integrable, then you can swap. There is a famous theorem for that. Okay? Fubini theorem. Fubini theorem tells us if the function is absolute integrable, you take absolute value, integral, limit bounded, then you can swap to integrals. Okay? All right. So here we assume we have that property. So here we like to swap these two integrals. Okay? The first one becomes second one. Second one becomes first one. All right? Yeah. So next line, we do that. Swapping. Okay? So next line. Look at the inside one from 0 to infinity, it becomes outside. 0 to infinity. This first one outside from s to infinity now becomes inside from s to infinity. We swap the order of these two integrals by Fubini theorem. Okay? The function value absolute integrable. Okay? So we can do that. It's a powerful theorem. Okay? All right. After we do that, yeah, so look at that. After we do that, yeah, so now, because, all right, when you swap integral, the dummy variable you also swap, right? dt, now dt outside, ds tilde inside, okay? ds tilde inside. So then t, ft, here, little s tilde becomes dummy variable. See? Becomes dummy variable. Okay? All right. So f of t, little f of t has nothing to do with little s tilde, right? F of t has nothing to do with little s tilde, so we can take f of t out. So you can factor little f of t out of the integral, out of the inner integral. Okay? So then inside integral, you can find its value, right? Yeah. This e function integral, you can find its value easily. Yeah. So next one, you find its integral. Okay? Yeah. Then by the definition of Laplace transform, it is Laplace transform of f of t over t. Okay? That's the proof. That's the proof of the formula. Okay? Yeah. Yeah. Change the order of two integrals. Yeah. And we can do it by that Fubini theorem. Okay? Yeah. All right. Yeah. So after that, now all these formulas we can apply in our computation. Yeah. 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 Here you can see where we have so many formulas. Yeah. So you may get lost, yeah. But after you study a little more, you try to get familiar with all these formulas. Okay? The basic formula, derivative, integral, all these commonly used formulas. Yeah. So you need to do a lot of practice. Yeah. Yeah. Especially in our homework assignment number 3, you need to do a lot of practice on these formulas. Okay? Yeah. Because we have 3 out of 8 questions in the final total 8. 3 of them, 3/8. Yeah. You can calculate 3/8. You need to apply these formulas. Yeah. All right. Next topic, E.3. Now we work on examples for differentiation and integration of Laplace transforms. Yeah. All right. Let me show you a few examples. integration of change. Here, all right. Yeah, so that's the formula, all right? So integration at the S domain. Yeah. New theorem, okay? New theorem. Yeah. All right. The first question, calculate inverse Laplace transform of this function, log, natural log of 1 plus omega squared over S squared. Yeah. Yeah, look at that, okay? Right. But that one, this function, yeah, you know, how do we try to, yeah, because here you can see one thing it's special in this example is the natural log. Yeah, the natural log. Yeah. In our basic formula, do we have the natural log? We haven't seen any natural log in our basic formulas, right? Yeah. But we know if you take a derivative of natural log function, then the natural log is gone, right? Yeah. Yeah. So you like to take the derivative. That means you may like to consider, you know, derivative of this function. That could be useful for this question. Okay, all right. Yeah. Yeah, so now, look at this. Yeah. Inverse. Yeah. So here, integration. So in order to apply the formula here, okay, or the formula here. So in order to apply the formula, yeah, here, all right. We want to imagine, so this whole thing, yeah, can we imagine as an integral of a special g function? Because we just want to match the form here. So we can inverse Laplace, we can find a little f over t, yeah. We can find a little g over t, right? Inverse the whole thing, Laplace, inverse the whole thing we want to match this structure. How about that? Yeah? All right, so here. Yeah. Inverse some function, okay? So that function, you know, a little complicated, yeah. But we want to apply the formula here. Yeah. This version, inverse, yeah, some S function. All right, but that function, we want to fit in this structure, integral structure. Is it possible we find an integral for this unknown g function? Capital G function is unknown. We need to calculate it. We need to find that capital G. Unknown g function such that after we take integral like that, we get this function. If we can do that, we can apply this theorem, this formula. Because capital G, if you know capital G, can you calculate little g by its inverse Laplace transform? After you get this little g divided by t, you get the answer, right? That's the way we apply this formula, okay? All right, so we want to find capital G first. How to find capital G here? Do you have an idea how to find capital G? Taking derivative, right? Taking derivative, yeah? Do you still remember fundamental theorem of calculus? Fundamental theorem of calculus. Fundamental theorem of calculus, yeah. Yeah, I put one in our basic formula, so that file, okay? Fundamental theorem of calculus. Based on that fundamental theorem of calculus, what's the derivative of this function? Derivative of this function. We take integral, then derivative. Do we go back to the same function? Because we take, yeah, so here, we get one arbitrary function. Now we take integral. After that integral, we take derivative again. Yeah. Do we basically go back to the original function? Yeah. But here, basically it's correct, all right? But one little thing you need to pay attention. The S variable appears at the lower limit, not upper limit. Lower limit, not upper limit. Okay? Lower limit, because fundamental theorem, upper limit is B, lower limit is A. Right? Yeah. Fundamental theorem. Upper limit is B, lower limit is A. So f of x equals ax little ft dt. Okay? Fundamental. If you represent in that way, what's the capital F derivative? What's the capital F derivative? Sorry, x. What's the capital F derivative by fundamental theorem of calculus? Little f of x. Little f of x. Okay? Yeah. But here, the variable x appears at upper limit. Upper limit. So we have this. But here, the variable s appears at the lower limit. It's different. Lower limit. Lower limit, because you need to use upper limit minus lower limit, right? Upper limit minus lower limit. Okay? Yeah. So lower limit, you minus lower limit. So in front of lower limit, you have negative sign. Lower limit is minus. Okay? All right. So when you take derivative, if you see lower limit, you should use negative g function, not a positive g function. Okay? Negative g function. A negative sign comes from the lower limit. Okay? Upper limit, you use a positive sign. Okay? All right. So negative capital G of s equals the derivative of this natural log function. You write in this form. Its derivative is easy to calculate. Right? Yeah, derivative. Easy. Natural log is gone. Okay? Yeah. After simplification, you get a g function equals this expression, g function. Can you calculate little g from this function? By inverse Laplace transform. Inverse, yeah. Cosine, right? Constant 1. Cosine, constant 1, right? Yeah. Basic formula 1, yeah, for this one. Cosine, yeah, cosine, right? Yeah. So inverse Laplace transform of capital G, little g, 2 minus 2 cosine omega t. Yeah, cosine omega t. Okay, yeah. So after you get a little g divided by little t, you find original inverse Laplace transform by this formula. Yeah? So that one more step, because now we want to find the inverse Laplace transform. Yeah. All right. Because that's the g function. We have this capital G function. And by this formula, it should be little g of t over t. Little g, that function, we copy, we get here. Okay? Yeah. So look at how we apply these formulas. Yeah. Think about it. So you need to, after you understand these formulas, the main thing, in order to use the formulas correctly, you need to identify the structure. You need to quickly identify. So what structure I want to use? Yeah. Okay. And what formula? The main formula here. The main formula is this one. Okay. You need to also identify the main formula, so you can. So when you do preparation, you already have the main formula in your mind. So you set your target. This is the target. Okay? All right. So then you can do the remaining steps. Yeah. So you need to have a, global view. Yeah. Then you need to try to address the details. Okay? Yeah. All right. Yeah. So that's, we have 3 slides. Yeah, but I will complete it next time. Yeah.